Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're evaluating beam deflections using moment area methods. In the next example, we have a beam with an overhang and a point load P at the end. We're asked to determine the deflection at the free end in terms of P, the length of the beam, and its stiffness EI. So we'll solve this example symbolically. As always, I like to sketch the deflected shape of the beam and figure out how to apply the moment area theorems. We'll draw a reference line for the undeflected shape and then try to visualize how this load will cause the beam to deflect. The point P is pushing downward, so we expect the end of the beam to move downward. We expect the middle part of the beam between supports A and B to deflect upward. So we'll get something like this. Okay, the distance that we're looking for, the deflection at the end, this distance right here, I'll label that as delta C. Okay, we also need to figure out how to apply the theorems by drawing appropriate tangents. I always, with a simply supported beam, I like to draw a tangent from point A. So I'll draw a tangent line from point A all the way out to point C. And that distance we can label as T at C with respect to A. So we could evaluate that. We may consider evaluating theta A, but we can't evaluate theta A directly in this example because we cannot say for certain if there's another point on the beam where the rotation is equal to 0. So a better way to find the relationship between T at point C and delta C is to also consider the tangent at point B, or the distance at point B. So I'll label this distance right here as T at B with respect to A. Okay, so notice by similar triangles that T at B with respect to A divided by L should be equal to this distance right here divided by 4/3 L. And based on that, I have enough information to solve for delta C. Delta C will be equal to T at C with respect to A minus this distance right here, which according to similar triangles is 4/3 of T at B with respect to A. So we need to evaluate both of these two tangents. Okay. In order to evaluate these terms, of course, we need the moment diagram. I'm going to take a big shortcut in drawing the moment diagram for this beam. Of course, the systematic approach always applies, and you're encouraged to use that when all else fails. I try to imagine just for a minute here. We know that this point load pushing down on the beam on the overhang is going to cause linear moment to increase linearly out to support B, and it's going to be a negative moment, which is equal to, at point B, is equal to a value of PL over 3. Okay, so that's the moment diagram for the overhang. Now between points A and B, there's no load on the beam, the shear is constant, the moment is also linear, and the moment is 0 at point A. So we know that the moment diagram between A and B also has to be a straight line, which I will simply draw between the 2 points. So that is our moment diagram for the whole beam. And I took a big shortcut in order to get that. Okay? To evaluate T at C with respect to A, I consider the entire area, the entire moment diagram for the beam. So I'm going to divide it into 2 areas. I'm going to call this area right here A1, which has a centroidal location right about there. I'm going to call this area over here A2, the central location, a centroidal location right about there. Let's calculate those areas. A1 is equal to 1/2 times the height, PL over 3, times the length, which reduces to PL squared over 6. A2 is equal to 1/2 for the triangle, PL over 3, times the length, L over 3, which reduces to PL squared over 18. Okay, to evaluate T at C with respect to A, we also need our centroidal distances. The first one is going to be the distance from the centroid of area A out to point C, which is out here. So I'll call that x1, and that is equal to L over 3 plus the length of this overhang, L over 3, which is 2/3 L. Distance x2 is from the centroid of area 2 over to point C, and that x2 is equal to 2/3 of L over 3, which is equal to 2/9 L. Okay, so now I have everything. I can calculate T at C with respect to A is equal to A1, and everything is negative because the areas are negative. PL squared over 6 times x1, 2/3 L, plus area 2, PL squared over 18 times 2/9 L. And then, of course, this is going to be divided by EI. But we need to reduce these fractions. So pull out PL cubed over EI since it applies to all the terms and the negative value. Okay, so I have 2/6 reduces to 1/3. I have 1/9, and then I have plus this term also reduces to 2/18 reduces to 1/9. So I have plus 1 over 81. So I'll multiply the first term by 9 over 9. And so I get negative 10, 9 plus 1, 10 over 81 PL cubed over EI. Okay, I also need T at B with respect to A. For that term, I'm only going to consider the moment diagram in the area between points A and B, which is the triangle 1 with area A1. And this time, my centroidal distance, x is from point B to the centroid of that area. So I'll call that x1 equals, in this case, is just L over 3. Okay, so I can evaluate T at B with respect to A is equal to the area, which we already calculated. That area, PL squared over, it's negative, PL squared over 6. I'll throw in my EI here, and then times x1, which is L over 3, and I get a negative PL cubed over 18 EI. There's my negative sign. Okay, so finally putting it all together, I have what I need to calculate delta C. Delta C is equal to T at C with respect to A, negative 10 over 81 times PL cubed over EI, minus a 4/3 T at B with respect to A, which is negative PL cubed over 18 EI. Okay, so I'm going to give myself a little bit more room here. Erase some of these terms. Okay, so what I have here, I'm going to pull out a PL cubed over EI, and I have negative 10 over 81 plus, these two negatives cancel, plus a 4 over 18, or that's 2 over 9. Okay, reduces to that. Now I have 81, and 3 times 9 is 27, so least common multiple is 81. I need to multiply this by 3 over 3. Okay, therefore I have negative 10 plus 6, which is going to be negative 4 over 81 PL cubed over EI. And that complicated problem reduced to a nice, elegant, simple result, and that is our deflection at C.